Hi, my name is Kyle McCall, and I'm a new assistant professor of material science and engineering. I got my PhD in applied physics from Northwestern University under the guidance of Mercuri Kanatzidis in chemistry and Bruce Wessels in materials science, and I looked at the characterization of single crystal metal halides for radiation detection. I then went to ETH Zurich prior to arriving at UTD and worked under the group of Professor Maxim Kovalenko developing new metal halides, including halide perovskites, for radiation detection and light emission. My work at UTD will focus on the design, synthesis, and characterization of complex semiconductors for energy-related applications, such as light emission or solar energy conversion. This work will encompass the full range of materials chemistry, from the choice or design of prospective energy-related materials to their successful incorporation into functioning devices such as solar cells or LEDs. This ranges from relatively straightforward directions like developing or altering known compounds to improve performance, perhaps by doping, to larger challenges such as being the first to grow large single crystals of compounds which previously have only been made as powder or as nanocrystals, or even conceiving a new compound and being the first person on the planet to solve its crystal structure and see what it can do. I'm particularly interested in improving our understanding of structure property relationships in optically active materials with chemically soft and harmonic bonding. For example, the 3D halide perovskites have taken the research world by storm thanks to benevolent properties such as defect tolerance, which are partially a consequence of the dynamics of this three-dimensional crystal structure. Basically, the 3D network of these octahedra vibrates and moves dynamically in response to charge or optical excitation, and this has important consequences that lead it to be a very good solar cell material. If we change the dimensionality of this crystal structure, so if we take this 3D network and start to slice it up into 2D, 1D, or zero-dimensional units, this has drastic consequences because it disrupts these dynamics. And so you will find different optical characteristics that we don't fully understand or don't always understand. And this is because the interplay of electronic and vibrational states in such low-dimensional materials is very complex. So if we take the simplest case, such as a zero-dimensional metal halide, which has fully isolated metal halide octahedra with an organic spacer, how do we design it so that it has the most efficient light yield? So the hope is that we have this organic spacer which spaces these octahedra enough that an optical excitation of the octahedra will stay within the same octahedra and not transfer the energy state for a chance of loss, and then immediately recombine and lead to luminescence. So if we want to achieve this, how large do the spacers have to be to improve the light yield? How does the rigidity of these spacers affect the excited state dynamics? As a materials chemist, my goal is to explore such relationships experimentally by making a series of chemically similar materials and then rationally designing compounds based on what we learn from such series. I'm also very interested in developing mixed anion materials, basically how to combine the benefits of materials like halide perovskites with their dynamic bonding by incorporating also elements such as oxygen or sulfur, which are often lead to higher stability semiconductors, such as the oxides and chalcogenides that are generally used for other optical applications. This work is inherently cross-cutting, as the interplay of chemistry and physics is crucial to determining the structure property relationships that underlie the behavior of these compounds. These synthetic efforts and basic characterizations will be the primary focus of the McCall group, with collaborations for advanced characterization to fully realize this interdisciplinary research program. This work will illuminate the key structural features underpinning anharmonic optoelectronic semiconductors and build on these principles to develop new materials for energy-related applications in solar cells and light emission.